So the next talk on what I'm calling this geometry analysis overview is about a new, not just one new feature, but it's really about a handful of features, really three core features that work together to be really powerful. And I'm really excited about this capability for VSP, but I'll be honest, it's a lot of moving parts. In order to make use of this, you have to set a lot of things up. You have to set up an analysis. You have to set up some auxiliary geometries, which you guys don't know what they are yet, and you have to set up some new geometry types. And so there's a lot of things that have to be in place to make this work, and it's probably not very discoverable, if not very intuitive, if you haven't seen this kind of a talk. So hopefully today in the morning sessions and then in my later in the day sessions, I'll be able to explain how this all fits together. And really the purpose of this talk right now is to give you guys the big picture view. Let's give some context about how all these things work and why they're the way they are. And then we'll come back later in the day and we'll do a deeper dive into the nitty gritty of each of the different steps. So hopefully that context makes sense. And as I said, I'm really excited about what this can do, but there's a lot going on. So what we're aiming for is an ability to support what I'll just generically call geometry checks. And there's a lot of geometry checks in the aircraft design process that are familiar to an aircraft configurator. And all of these checks, in the old days were performed at a drafting board by the configurator, by the draftsperson. And today they're going to be checked by your CAD person, and they're checked in CAD. And checking these is a very manual process. You've got to go and, it's something that's typically not integrated, for example, into something like an MDO or an automated design process. These are a very manual thing. And they usually result in a qualitative result. Either you pass or you fail, and which a pass-fail isn't really suitable for use in an optimization process. And this manual process is actually, these tests are a lot harder than you think they are. And I'll talk about why, but basically the human is actually doing more in these tests than you probably think they are. So what are some examples of this? For example, here's one where you might want to check to make sure that the spinning rotors on a tilt rotor don't intersect with the fuselage. And so do those spinning rotors hit the rest of the aircraft? You also might want to check, do the spinning rotors hit each other? That would also be bad. And so in this case, you'll see I have this little red line showing the minimum distance between those. And in fact, there's going to be a tiny little red line. You can't see it from this angle right here. There's a tiny red line, which is the minimum distance between that rotor and the side of the fuselage. Other geometry checks, you might want to check that does the aircraft in the folded configuration, are there any interferences? Do these propellers hit the vertical tail? Does the nacelle hit the upsweep on the aft fuselage? Does everything clear, or is there any collision back there? Or just looking at the folded propellers themselves, do any of the blades, when folded, intersect with each other? Do they hit each other? And you can see that little red line shows the minimum distance between any of these blades. You might want to check that, do all the things inside the aircraft, all of the things that you've packaged, do any of them overlap with each other? So, is there any overlap between the flight crew and each other, or between the flight crew in this cargo bay? Are there any interference between those? And in this case, there's a little red line showing that the nearest distance between any of these components is between the elbows of the flight crew. Or you might want to check that, do any of the things that belong on the inside of the aircraft, do any of these things interfere with the fuselage? Do any of them protrude outside? Because you don't want the pilot's head sticking out the windshield. And you'll see here's a little red line showing the minimum distance between this cargo bay and the side of the fuselage. You also might want to check, earlier we were checking the propeller arc swing in the cruise configuration. You might also want to check it in the hover configuration. Does the propeller hit anything in hover? On a transport aircraft or a fixed wing aircraft, you might want to check, what is the tail strike angle? And so when pivoting about however the landing gear pivots during takeoff, what's the first part of the aircraft to hit the ground. And this is one of the cases where I say these techs are deceptively complex. See, when a CAD person is going to sit down and find this angle, they're going to visually look at the model and they'll immediately know that the first strike is somewhere here on the fuselage and somewhere to the gear, and they'll construct a tangent line between the fuselage and the gear. What they did implicitly, though, is they immediately decided that the first strike is not on the horizontal tail or the vertical tail or the engine or the wing or anywhere else on the aircraft. And that checking of multiple components is actually the hard part. And again, it's done implicitly without even thinking about it by the human doing this check. But when you want to go and automate this kind of check, to my knowledge, CAD programs, while they have the ability to construct a tangent line between one component and another that are specified by the user, they don't have the ability to find that line that's the first contact between many possible components. And where that component, which one is the sort of active constraining component, can change throughout the design process. So you also might want to check, the roll angle, rolling about the landing gear. What's the first contact point? Does it hit the engine or does it hit the wing? You might want to check the relationship between the center of gravity and the axis that you roll about. So here I've shown the tip back angle for the most forward, most aft, and the nominal CG location. We also have the tip over angle. So this is between the line between the main gear and the nose gear. And again, we're calculating the tip over angle between the most forward, most aft, and nominal section. You might want to check the ground maneuverability. So what is the turning radius of the aircraft? What's the ground track for the nose gear, the ground track for the main gear? And also then what's the furthest point and what radius does that arc does that sweep? And this tells you, how big of a hangar you need in order to do a 360 with the airplane. And here's another one where you might want to check the visibility. So from a pilot located at this position with some really terrible windows drawn here as subsurfaces, we can actually now go out and calculate what is the field of view in the angle. This is actually projected onto a sphere. What is the field of view that the pilot can see from that position? So setting this up, in the past, most analyses in VSP, things like CompGeom, they have very little configuration. There's only, one or two little things that need to be set up, and they're really easy to do. And usually there's only sort of one setup that you want to do per model. You want to run CompGeom, you're going to do it. If you want to find the wetted area of the aircraft, you're going to do that on the same set every time. And so not saving that configuration or not having a more complex way to deal with that is not really a big deal. Geometry checks, on the other hand, they kind of force a different paradigm. I expect that you're going to need a lot of geometry checks in a model. Just like we said on that transport airplane, you're going to have 5 or 6 or more geometry checks that you want to perform. On that tilt rotor, you're going to have lots of geometry checks that you want to perform. And so they also have a lot of subtle variations, little things, tweaks that you'll want to make, and we'll talk more about these, but adjustments that you want to make to it. And then you want to go back and revisit these frequently. You want to go back and rerun that tip back angle or that tail strike angle. You're going to want to run that over and over again. And so if there's a lot of fiddly settings and a lot of tweaking, you don't want to have to do that over and over. And so you could automate this just by scripting everything through the API, but there's a lot of people who don't use the API. And so what we've done, first thing that I'll talk about, is we actually now have a manager in order to work with these geometry analyses. And so basically it's this is a GUI where we set up different run cases. And so this geometry analysis GUI, we have the list of different analyses and then all of their settings. It allows you to set up and manage a whole collection of these analyses. And each one has a primary and a secondary geometry where that can either be defined by a set, a mode, or a geom. And then all of the different analysis options, all the different settings to make them work, and anything else to sort of work with that is in this GUI. Also, it makes it easy to visualize the results and to dig deeper. Lots of times, these analyses will calculate a whole bunch of different things. A whole bunch of different numbers will come out of it. And so, rather than just show you a single scalar, you can dive deeper into these analyses. So that's what I'm talking about, the geometry analysis manager, and we'll dive deeper into that in a minute. But that's sort of the setup there. You may have noticed that a bunch of these analyses that I just talked about, and if you're a configurator, a lot of these things revolve around the landing gear of the aircraft. And so, in the past, people have built landing gear models of their own airplane, but usually they do it, with just a bunch of stacks or fuselage components. And rather than doing that, to make this really work, we need a dedicated landing gear component. And what this does is, because it's a dedicated landing gear component, that means that my analyses that I'm building for you, these analyses can know that, hey, this thing is a landing gear, and so it should behave like a landing gear. It should rotate about the gear. The gear can be castered or not. It knows about the contact points. It even will know things like a tire can deflect, and it's either going to be sitting at the static loaded radius or the first contact point, or even a flat tire where it's riding on the rims of the wheel. These are all things that it can know about the fact that it's a landing gear. It can know that the strut is compressed or the strut is extended. And then it needs to know about the center of gravity envelope. So all these things need to be built into the landing gear. And because of that, I've built a new landing gear component for VSP. Some of these checks that we're going to do are done on a part of the geometry that's not really an explicit part of the geometry. And so, for example, the arc that a propeller swings through, including some flapping angle fore and aft, that propeller arc is not an explicit model of the geometry, right? That's not something that you model, I mean, you could if you had to, but it's not something that you should have to model in your aircraft. But instead, it's something that, given the definition of the propeller, I have enough information to just be able to quickly generate that propeller arc swing for you. So without you specifying much more information, you only have to specify the forward and aft flapping angle. I can take what you told me in the propeller, and I can build that propeller arc swing or that burst cone. If you want to look at, okay, if I throw a prop and I need to look at a 15-degree angle in front of and behind that rotor, that burst cone, again, you don't have to build that geometry yourself. I can build that using what you already told me about the prop. And this is true across the board. Things like the landing gear, it's one thing to define the landing gear state, but lots of these checks need to be performed in an off-nominal landing gear state. So either a flat tire, a compressed oleo, an extended oleo, tire on one side flat, but the other side is extended, sort of worst case scenarios. And so all these off-nominal landing gear are also things that we can work with. And so this general concept, which is these geometries that we're going to define based on another geometry, we're going to call these the auxiliary geometries. So there's three concepts I've hit. We've got the geometry analysis, we've got the new landing gear component, and then we have the auxiliary geometry. And so that's sort of that background. And I'm going to quickly just go in and do a little bit of a demo to again, just give a teaser. But again, this afternoon, I've got two really deep dives into this topic that should go into more. Okay, so, and I see a bunch of chatter in the chat. I'm thrilled that people have the same enthusiasm for this that I do, and I think that you guys are nailing the use cases and how they relate to modes and these other features and how all this stuff comes together. So let me just open up, for example, that tilt rotor model that I kept talking about, why some of these things would make sense later today. So let me shade it and come in here. And just as an example, again, this is all set up for us, but if I come in now, oops, you know what? I ran the wrong version of VSP. Let me look, I have to run the version that actually has all these features in it. So, and hopefully I didn't hit save earlier and lose all those settings. Let's just make sure that it's still all in here. Okay, let me come in here into the geometry analysis. And you can see I have a whole bunch of these geometry analyses. And so, um, you know, cruise prop is a geometry analysis. And let me just show only that state. And so what you can see is we've now applied that mode and shown the auxiliary geometry. And so what we have here is the cruise prop interference is, does the auxiliary geometry of the propeller clearance geometry right here called propeller clearance, does it interfere with any of these components that it shouldn't interfere with? So does it hit the wing and does it hit the body? And let me just come in here over to this one and I'll say, let's evaluate that analysis. And so we've just done that calculation and you can see there's the little red line that shows there's the closest approach. And I'll show you what it does when it violates that later today. But, we can just go through and I can show, here's the propeller clearance. Do they hit each other? If I want to check the stowed configuration, here's the components that are involved in checking the stowed state. And so let's evaluate that analysis. And you can come and you can see that right now the minimum distance is between the nacelle and the little ducktail back here on the fuselage. And, we can go through and show all of these if we needed to. We can evaluate all of them. Some of them aren't evaluated right now. We'll just show a couple more. So here's the propeller, the mutual interference between the props to make sure that your fold solution is good. Here's the packaging. Do the things that are supposed to be inside the airplane, are they inside the airplane or do they protrude outside? And here, the minimum distance between these things and the outside of the airplane is this little red line here. Here's the mutual packaging. Do the things that are supposed to be inside, do they overlap with each other? So here we can show, the minimum distance is the elbows of the flight crew. And, here's my, does the propeller in hover, does it interfere and hit anything? So there's the analyses that are set up in this model. Again, we'll do a deeper dive later today. Let me open up that transport model just so that you can see what the same kinds of things that it does. So here's that model with the landing gear, and you can see we've got our flight crew and some really terrible windows. And we can come in and we have all of these different analyses. I'm going to evaluate them all just so that it'll go through and run all the calculations. That way I can quickly click between them. But let's show only the things that are involved in tail strike. And so you can see the tail strike, we're pivoting about the main gear. And then there's that angle of nearest approach. And if I want, I can even apply that rotation to the landing gear and I can show that this landing gear is rotating about the pivot of the bogey. And that's then what the ground plane looks like when it hits that tail strike. And that's an off nominal landing gear that we're looking at that with. We can show, here's our tip back angle, which I'm still showing in the off nominal. So let me, here's our 2-point ground mains. Let me come in and change that bogey angle back to 0. And so here's our tip back angle calculation with a vertical line shown in the most forward, most aft. Tip back angle calculations. I see someone just asked if that they don't see this in their version, and you're correct. This is not yet released. This is a preview of something that will hopefully be released. I'll call it within the next month or so. This is almost ready for release, but it's not out there yet. Okay, we can look at our roll strike angle. So here we are, we're pivoting about the right gear in this case, and we're finding what's the angle that we first hit. We can come in and look at our tip over angle. So there we're rotating about the right gear and the nose gear. And again, with the most forward, most aft and nominal CG locations to find those rollover angles, tip over angles, sorry. I actually calculate, this one's not very graphical, but I calculate the distribution of weight on the main gear. So it reports out what's the fraction of weight on the nose gear. So in the nominal CG location for this configuration, 8.5% of the weight is on the nose gear. I calculate the turn radii. And, what's the ground maneuverability? We have, the ground and ceiling clearance envelope. So in this case, it's the distance between the ground, the lowest part of the aircraft, but also the distance between the ground and the highest part of the aircraft. So you can, how tall does the hangar need to be for you to fit in that hangar? Here's a neat one. If you're landing a narrow body transport on an aircraft carrier and you need to know, does this aircraft, hit any of the equipment on the deck of the aircraft carrier, you can put in a profile that represents all of those obstacles and the user supplied profile, and then we'll check, do you hit any of those things? And finally, the last one I'll show here is a pilot visibility check. So here what I've done is we've actually come in and we have the pilot and we have their nominal eye point, the design eye point, which is just the average between your two pupils. And we've drawn some really ugly windows on this aircraft as subsurfaces, but then we found what is the field of view of the pilot through those two windows. So we can see this is what is visible for the pilot from those windows, and we can use those to check all kinds of visibility checks. So, yeah, so again, there's going to be 2 more deep dives. I'll just go a little bit deeper just to say that all of these things, let's go to say the carrier envelope, let's show that one. So this is based on, right, this carrier envelope is a special kind of off-nominal state of the landing gear, and that's the CCE ground. And so there's other parameters involved in it. For example, there's a parameter to control how far off of axis the main gear is placed. And so this model is, I believe, in feet. And so there's a requirement that I've seen that the Navy says you have to be able to, the main gear can be off axis by as much as 24 inches. And so if we put in 2 feet, that places the main gear off axis by that. But then you might also have a problem where one of the landing gear, the suspension instead of nominal is compressed. And so there we've compressed the left gear. And, the other gear, the opposite gear is extended. And on the compressed side, the tire might be flat. And so you can see that if with these gear extensions and a flat tire, we're actually already hitting the nacelle. But what you can do is you can set up this off nominal gear location, and then we can come back in and we can run that analysis. And what it'll do is it'll come back and it'll tell us, that we interfere. And you see this red volume down here. It's actually calculated how much of the model violates that state. And so you can see that this isn't just about the nominal landing gear, but about all of these off nominal conditions and being able to quickly control them and check all of these different checks. So I'm going to stop there. I'll go back to the chat if anybody has quick questions. Like I said, later in the day, this talk that I give after the second break is going to be a deep dive just into the landing gear and all the landing gear related analyses and auxiliary geoms. And then after that, I'll do a deep dive into the geometry analysis manager, and then also talk about all of the other checks, which is going to be a lot of. So this one will mostly be the transport airplane cases that I showed, and this one will mostly be the tilt rotor aircraft cases that I showed. So we'll do a deep dive into both of these subjects where we'll cover a lot more detail. And then the last talk of the day, Max is going to do an actual talk about a demonstration case where he's been using attributes, modes, and geometry analysis to do an actual design study and optimization study as a demonstration of all these new features. So we'll get to see what Max has to say about that. So that's kind of the story arc for the rest of the day on this topic. And not to sell the VSP Aero stuff short, I'm actually incredibly excited about this stuff too. Also not released yet, but hopefully very, very soon, this VSP Aero stuff. So today is really a big preview of things that are going to come. So Zach, you asked what comp geom and what section is used for the rotor blade volume. I'm not sure how to understand that question. I assume that we were at least talking about the tilt rotor model. And here, are you talking about the, if you could clarify your question, I'll try and answer it. Okay, great. Glad I answered that. Um, Also, Keith, I saw your question about the windows. So, and so we'll talk about that more when I talk about the pilot visibility geometry check. Certainly, in terms of, making something transparent, making this fuselage, that's just choosing this material. So here I've chosen it to be, semi-transparent. So you can choose it to be glass. You can choose the whole thing to be ruby is one of my favorites. It's a nice shiny red. You can also make custom colors. So you can come in here and customize that material. If you like the ruby, but you want it to be transparent, you can dial in. You can dial in transparency on any of these colors, and you can save that and give it a name. Now, obviously, that's applying to the whole thing. Um, in terms of windows for doing that analysis, what we're going to do is we're going to apply subsurfaces. So we can come in here and basically we draw a rectangle as a subsurface. You can see here it's in red. Turns out turning this to ruby when I was going to demonstrate something in red was a bad choice. So let's go back to glass light. So our subsurface, this rectangle, what we're doing is we can move it around. So this rectangle is drawn in those UV coordinates that I was talking about during the geometry talk yesterday. And so we can basically draw this as a rectangle that we then, it's a rectangle in UV coordinates. But so we might be able to use that to then represent a window. And, again, this is a pretty ugly window. Another preview that we'll see here later today is we now have the ability to we have much more flexibility in how we design subsurfaces. So I won't spoil my own thunder there, but there's going to be a lot more. But yeah, so what you can do is you can draw a window like that using a subsurface. And again, it's not showing this is transparent and this is opaque, but it does show that window. And then now when we do the analysis for the visibility, it can actually cut out that window and project that forward.